Hi, this is the second video of this series, and it should be used alongside our article that is published in the Journal of Applied Behavior Analysis entitled A Primer for Using Multilevel Models to Meta-Analyze Single-Case Design Data with A/B Phases. Both the article and the data sets, the actual Excel files that I use in this tutorial, can be found on the Java website. This particular video, I'm going to show you how to run the regression analysis in SPSS. I use version 26 to conduct the multi-level model for single case design data. The data I'm using here were prepared in a certain way, and I showed how to do that in video 1. So if you are following along with the actual data, you might want to go ahead and prepare the data first before tackling this one. Now, the purpose of the regression here is to generate an effect size for each of our cases. So the general question we had with our data set was, what is the impact of DRL schedules, differential reinforcement of low rate behavior schedules? What is the effect of those DRL schedules on behavior? And typically, when we conduct a single case design study, we will interpret those results visually. So there's not a single effect size number, like this is the overall effect for this particular person, that is reported alongside with that data. And even if it is, it might be a different effect size metric across these different studies. So in order to run our meta-analysis using the multi-level model, we need some sort of standardized effect for everybody so that we can summarize those effects. The effect size that we are using is called G, and that can be calculated based on the results of the regression. Hence, I'm showing you how to run the regression to ultimately get G, and I'll talk more about how to calculate G in the third video in this series. Okay, so let's get started. This is the data file that I prepared in the first video, and note that some of the cases are filtered out. These little diagonal lines that go through the numbers here means that it's filtering out those ones. It's not going to use them in the analysis because for our data set, we're only looking at one type of DRL schedule at a time. So for this analysis, I'm only looking at the spaced responding DRL, but we would use the same steps for both types. We would just filter out the different kind. First, let's start with Y. So Y is right here. Y is the outcome variable, and it was measured as the rate of responding, of whatever the response happened to be for these different studies. We extracted the Y values using a program called ungraph from each of the figures for each of the participants in each of the studies that we use in this analysis. Now here in this Y, this appears in the scale that the authors chose to use for that particular study. And so there was some variation there, and we needed everything to be on the same metric. So some of them might have been, for example, responses per minute. Some might have been measured as responses per hour. Others were just as a total count. And a few of them used inner response time. So all of those things, we can recalculate them so that we can get them all in the same metric. And we chose to put everything into responses per minute. So just a couple columns over where it's labeled YRPM is where we actually converted it to responses per minute. So that is our primary outcome variable for the analysis. The next column you need to know about is X, and X is simply the session number. However, the original article labeled it as the observation or session number on the time series graph that they displayed. That's all that refers to. Now, in the multi-level model approach and the regression approach, it's useful to convert X so that it is centered around 0, because 0 has a very particular meaning in regression. It just allows to have more meaningful interpretations of the data. So what we ended up doing was converting all of these X values so that 0 had a very particular meaning. And our meaning was the transition from baseline to treatment. And so to do this, you come over to the time variable here. So for time, what we did was made the last session of baseline equal to 0. So for this participant, so this is participant 1 of study 10. I'm just going to highlight them. And this is session number 8 for them. But this also happens to be the last session of baseline. And the reason I know that is because this phase column that's right next to it, that tells us whether it's a baseline or a treatment condition. Baseline is 0, treatment is 1, so this is the last 0. So this would be labeled as a 0, and then all the preceding baseline sessions are ordered in or numbered in reverse order, so negative order here. And then each treatment session starts with +1 and then moves forward until the last session. So it's actual session 28, but we would have labeled it as session 20. So we did this for every single case, and that was done ahead of time. So that's the time variable. I already kind of told you about the phase variable, but just to reiterate, phase is the treatment condition. It's whether we're looking at a baseline condition or the DRL condition. Doesn't matter what type of DRL, it's just the treatment condition. And we coded that as 0 or 1. And then last, the time phase variable. This is the interaction term, and it tells us whether the effect on behavior or outcome varies as a function of the combination of time and phase. So for example, is the trend over time throughout one of the phases different in the baseline versus the treatment phase? And this is literally calculated by multiplying the time value by the phase value. And so that's how you get time phase. Here is the regression equation, and this regression equation is based on those 3 variables, time, phase, and time phase that I just told you about from the spreadsheet. The regression equation predicts some sort of outcome, typically labeled as y. Here I've labeled it as behavior because ours is behavior or rate of responding. And then that outcome is predicted based on certain predictor variables. Again, our predictor variables are time, phase, and time phase. So for each of those variables, we have data on them. And what the regression equation is trying to do is figure out what the slope or relation is for each of those predictor variables. So pi is the slope. Now in standard regression, we usually call the slope b or beta, but for the multi-level model approach, we use the notation of pi. So pi is the slope, and that describes a relation between that particular x, that predictor, and the ultimate outcome, or y. Now imagine real quick that we have a very simple A-B phase graph where our A phase is baseline and our B phase is DRL or some sort of treatment. Each of those pi values has a very specific meaning within the analysis of this A-B phase graph. So pi sub 0, that is called the intercept. And because of how we coded our predictor variables, how we coded time and how we coded phase, what means 0 within those, pi sub 0 ends up being interpreted as the value of the last baseline session. Pi sub 1 is the time variable, and this is interpreted as the slope of the line in baseline. So it tells you how much behavior changes over time, but just in that baseline phase. Pi sub 2 is the relation of the phase variable with the outcome, and it can be interpreted as the difference between baseline and DRL. So this actual difference between the last baseline session and the first DRL session. And finally, pi sub 3 is the difference between that change in slope between the baseline condition and the DRL condition. So that interaction between both time and phase. And then E is error. So for our purposes, and I think for most people, behavior analysts that would be interested in conducting a multi-level model, they'll be most interested in the phase and time phase variables. They want to see how much does this intervention or condition change behavior, and is the slope or trend of the data different in the two different conditions. So those are probably going to be the most interesting for us. Okay, so let's actually run the model. So I'm going to start by going to Analyze, scroll down to Regression, and then Linear. We're running a linear regression. We need to identify what our dependent variable is. So the dependent variable is the outcome, and our outcome is Y responses per minute, the rate of behavior measured as responses per minute. And then in this box labeled independence, this is where our independent variables or predictors go. And we have three predictors: time, phase, and time phase. So we move all three of those over there. Now we can go through and select different options if we want, but the standard default options that SPSS gives for the linear regression are really all we're going to need to calculate our effect size G. So I'm not going to select any of the extra options. I'll just hit OK. Here's our output from the analysis. This first table is simply telling you for each case what variables were entered into the analysis, what the predictors were for the analysis. Now notice for this regression how it almost looks like it's repeating over and over, and that's because we had the different identifiers. These are the different participants within each study, and this is how it splits the data out in the output based on each of those people. So this is 201, 202, 203, etc. We can scroll past this first table. It's not very interesting. The next table is the model summary, which tells you what proportion of variance in the outcome can be explained by the predictors we used. And this is what the value R squared refers to. We're not using this for calculating G, but just to let you know what that is. The next table is the ANOVA table, and this table is the test of the R squared value from the prior table. So this table we are actually using, and I'll talk more about that, how we use it, in the third video, but just so you know, we will end up using the ANOVA table. And the last table is labeled coefficients. This is telling you the value of beta, or B, or slope, or for our equation, pi. So the coefficient table is the value of those slopes and then the test of whether that's a significant effect. So we'll be using data from this table as well to calculate our effect size G, and again, I'm going to describe that in the third video. So that's how we run the regression for each data set, and a quick overview of how to read the output. Now, as I said in the next video, I'm going to show you how to reformat this output so we can really easily work with and extract the estimates that we need, and I'll show you how to calculate the effect size.